So welcome to part 4 of lecture 28. In this part we want to kind of look at some classical results from geometry. And at first glance it may seem like these results are special to the plane or three-dimensional space, but they're actually coming from the fact that you're working with an inner product space. So we're starting with an example here, just a picture, where we have my vector u and my vector v, and I'm looking at the sum of u plus v. And if you stare at this, you know, the picture here kind of shows that the length of the vector u plus v, which is another way of saying the norm of these vectors, is less than or equal to the length of u plus the length of v. Right? So one way of thinking about this is just saying that the shortest distance between any 2 points is the direct path. Okay. Now this looks like something special about R2 and using length in R2, but it turns out to be that this is actually what's called the triangle inequality theorem, which means that it's true for any inner product. So the sum of two vectors and taking their norms is less than or equal to the norm of each, the sum of the two norms. And let me walk you through the proof of that. So we're going to look at the squares. We're going to kind of look at the squares here. So let's take u plus v and square it. Okay, so by definition, that's the inner product of u plus v with itself. And using the properties of inequalities, we can expand it out. And remember, we have to pay attention to the order when we expand it out. And so let's kind of clean this up, what we have. The first term is the norm of u. The second term we'll leave as the inner product of u and v. And the next term, we can switch it around, but we can take the conjugate of that term. And then the last term is the norm of v. Okay, and I claim that this is then equal to the norm of u plus 2 times the real part of the absolute value of u and v plus the norm of v squared. Okay, so let me just kind of justify in this particular result right here. It follows from this stuff that I've written in red. If you take a complex number and then you take its complex conjugate, when you add these two numbers together, you end up with 2a, right? Because the bi and the minus bi cancel each other out. So this number is the complex conjugate. We're adding the norm, the inner product of u and v to its complex conjugate. So we're just going to end up with the real part of, twice the real part of the inner product of u and v. And the real part of complex number is a, which is less than or equal to the absolute value of the a squared plus b squared. Okay, so we make the substitution. Actually, I don't need the absolute value here. I need it further on. Okay, so 2 times the real part of the inner product of u and v by this result means that I can replace it by 2 times the length of this complex number uv. Okay, so that's what I'm doing right here. So this is the real part, and then this is bounded by this part. And now, where can I go from there? Well, from here, I can use Cauchy-Schwarz because I can bound this number right here. Right, so this is less than or equal to the norm of u plus 2 times the norm of u times the norm of v plus the norm of v squared, right? So this here is, I'm using Cauchy-Schwarz. I'm comparing this quantity with this quantity. And then if I look at the what I have here, this is actually, I can factor it as the norm of u squared plus the norm of v squared. Oh, sorry, put the squared in the wrong part. It's the norm of u plus the norm of v squared, right? So when I expand this out, I get this term here. And then I compare the first and the last terms, and I cancel off the square roots, and I get the desired inequality of the triangle inequality, which is, you can still see up here in black. Okay, so this is something that holds in any inner product space. And it turns out that like a lot of classical results from geometry kind of can all be expressed in terms of inner products. We already saw that with the Pythagorean theorem. Here's another example, classical result from geometry. if you have a parallelogram with one side A, so the other side would have length A, and the other two sides have length B, and if C is the length of this diagonal and D is the length of this diagonal, then you have the fact that C squared plus D squared is equal to twice A squared plus B squared. Okay, and this is called the parallelogram, and I don't know why I put inequality because it's inequality, parallelogram equality, which is more generally saying that taking any two vectors, the sum of those two vectors and their norm squared plus the difference of those two vectors squared is equal to twice the norm of the u squared plus the norm of v squared. And why does this kind of follow here? Notice that you want to think of the vector A as corresponding to a vector and B corresponding to a vector. So on this side, you're getting the A squared plus B squared, and U plus B would be the vector C, and U minus B would be the vector D. Okay, and so let's just kind of hammer out the proof here. And again, it's just following the definitions and keeping track of all the properties that we've learned as we go along. So we expand out this term, and we expand out this term, right? And because we're doing squares, it just means the inner product of u and u plus v with itself, and over here we have u minus v. So we just, follow our nose and use all the properties that we know. The first term here looks like this. So that's the expansion of the first term, and then the expansion of the second term gives me, oops, that should have been a plus, gives me the length of u squared minus the inner product of u and v minus the inner product of v and u, and then plus the norm of v squared. And when you do your arithmetic, it all collapses to the desired result. Okay, so there we go. That's the parallelogram equality. Okay. So a lot of things from today's lecture. We learned about orthogonal decomposition, we learned about the Cauchy-Schwarz inequality, and we learned about things like the triangle inequality. So these are all things that you get once you have an inner product on your space. So that's it for today. We'll continue our discussion next time where we use inner products to talk about the Gram-Schmidt process, which you would have seen in your first year linear algebra course. Okay, have a great day, and I'll see you in lecture 29.